chapter 6. What do stars and fireworks and flame have in common? If you spend some time outside on a dark night and let your eyes adjust, if the sky is clear, you will notice that the stars actually have different colors. You all know that fireworks can have different colors. If you look at the flames from a Bunsen burner or a fireplace, you'll see various colors of orange and yellow and maybe reddish. If you look at a stovetop when you turn it on, it eventually becomes a very, very dull red and maybe a brighter orange, perhaps even a brighter red. But it goes through these color changes. These color changes represent, among other things, an indication of the temperature of the object that is producing that color. So we know something about the temperature of stars from the star's color. We know something about the temperature of different parts of the flame from its color, the blue and the white and the yellow and the orange and the red. And from a stovetop, we can determine its temperature from the color of the heating element as electricity goes through the heating element, producing resistance, and the resistance creates heat. And then the heat, of course, is what we use to cook with. In any case, we see that wavelengths depend upon temperature. In other words, every single color in the visible spectrum has a different wavelength. Of course, there are wavelengths beyond either side of the visible spectrum. And we can also say that wavelengths, since they're inversely proportional to frequencies, we can say that the frequency it can help us determine what the temperature is. So I want to back up a little bit to our electromagnetic spectrum and have you look at the scale on the diagram here in 6.2. Notice that the top scale is a scale of frequency. And notice that the frequency is going down as we go from left to right. And then the bottom scale, when we look at the bottom scale, we can see that the wavelength is going up as we go from left to right. That means that wavelength and frequency are inversely proportional. Of course, you should know that because the speed of light equals wavelength times frequency. And when the wavelength goes up, the frequency has to go down because the speed of light, c, is a constant. Another thing that you should recognize when we were talking about being able to predict or state in order the different parts of the electromagnetic spectrum is that as we go from the visible spectrum right here, the energy increases because ultraviolet can burn your skin or cause skin cancer. X-rays are going to go right through skin and muscle, but not bone. Gamma rays have enough energy to go right through you and even the earth at the high energy gamma ray photons. So the idea here is that energy is going up as we go from right to left, or it goes down as we go towards the red end of the spectrum. And so you'll notice then that the energy is proportional to frequency. And that's this equation right here. Energy is proportional to frequency, or we could say energy is proportional to nu, and our proportionality constant is something called Planck's constant, which we'll talk about in a minute. So the greater the frequency, the greater the energy. The greater the wavelength, the less the energy. One other thing, by the way, microwaves and radar are in the same part of the spectrum, and I've sometimes wondered if you put a microwave oven, a miniature one, on your dashboard if you could interfere with a radar gun. Please do not try that at home. Another thought would be, what if we came up with a kind of microwave oven, but it was variable? And so let's say you could turn the dial of the microwave oven, and if you wanted to heat up your coffee, you could put it in the microwave part and turn the dial to the microwave. But let's say you wanted to pick up the Cardinals baseball game. You just turn the dial to KMOX radio. Or let's say that you wanted to see some pretty colors. You turn the dial the other way to visible light. Or let's say you wanted to increase your tan. Stick your hand in there, turn it on ultraviolet. Or let's say you needed to take a self x-ray because you weren't sure if you broke a finger or not. You just turned the dial to there. I don't think such a thing exists. Probably would not be safe. But be that as it may, let's continue on. Wavelengths help us to determine the temperature. So we can predict the temperature of different parts of a flame or different stars by looking at their wavelength. Now, white light, of course, is going to be a combination of all of these different kinds of wavelengths. Some are going to be in greater abundance than others. And so the wavelength of the most intense radiation would be related to the temperature. And you would get some kind of curve that would look like this. It would not be a bell-shaped curve, like we often think of, but you would predict perhaps a slightly different kind of curve where this would, you can't go beyond zero. You can't have negative wavelengths, but you can have increasingly bigger and bigger wavelengths. This is often called a Boltzmann distribution curve. You might predict a wavelength like that. Now, the other thing, though, that you might predict is that as the frequency gets greater and greater and greater, the energy should get greater and greater and greater, and you should have a graph that continually goes up and up and up and up. And we're going to see that that turns out not to be true at all. But before we get to that, let's talk about something called a black body radiation. As you probably have all heard of, there's such a thing in space. Usually we think of them as being at the center of large galaxies, like the Milky Way even, and maybe there are isolated examples of something that we call a black body. A black hole. A black hole is a region in space that is so dense, the matter is so dense that not even light can escape. And if no radiation of any type can escape, well, then it's going to appear to us to be black. So outer space can look black because there is no light coming from that region, or it can look black in certain spots because that happens to be a place where you're looking directly at a black hole through your telescope. Now, black body radiation then, if something is a true 100% black body, you would expect to see zero radiation because 0% of the light would be able to escape. Imagine that I had a wooden or a thick metal box like this, solid, a box that's open in the middle, and I line the inside, let's say, with black felt or maybe black painted cardboard or black paper. And then I put a little hole in here and I peer into the hole. I would just see black because all the light coming from the outside through the hole would bounce around in the inside and eventually become absorbed. That would be pretty close to a black body, but not perfectly a black body, because certainly some photons of incoming light would be able to exit, unlike a black hole. So theories predicted at the time, let's erase that. Theories predicted at the time, right here, and I meant to use the highlighter, that the intensity should increase continuously with decreasing wavelength. So if we made our graph right here. This gets confusing. There we go. If we made our graph and this was intensity, brightness of the light, and here was our wavelength. Let's go with red. And I'm going to see if I can erase this by hitting the right icon. Try that again. There we go. So if we have a graph here, and this is intensity or brightness, and over here is wavelength, you would think that as the wavelength is getting bigger and bigger and bigger, meaning the frequency is getting smaller and smaller and smaller, we should get a curve that looks like this. And of course, the software on this iPad immediately turned that into a straight line. So instead, let's come over here and look at a much better graph. So here's my wavelength down here. And here is the intensity right there on the y-axis. And as the wavelength gets smaller and smaller and smaller, the frequency is going to be getting bigger and bigger and bigger. This could also be frequency here, or we could use the letter F for frequency. And you can see that my graph is going up and up and up. And we'd expect it to continue going on up and up like that. At a lower temperature, you might expect your graph to go something like this. And an even lower temperature, you might expect the graph to kind of go like that. But that's not what happens. At a certain point, usually in the ultraviolet region, which is right here, all of a sudden it just goes to zero. All of a sudden here it goes to zero. All of a sudden here it goes to zero. That's called the ultraviolet catastrophe, because instead of the intensity of the light getting greater and greater and greater as the wavelength gets smaller and smaller and smaller, which means, of course, that the frequency is getting bigger and bigger and bigger. We'll put that down here. This would be a bigger and bigger and bigger frequency as the wavelength is getting smaller. That's not what happens. Now, before we move on and try to explain this, we should say that if you like astrophysics and astronomy, not only do the colors of the star indicate their temperature, but it helps us to understand that stars go through a life cycle. And stars can get very, very, very hot and can be white hot and even blue. And stars can begin to cool down and become red. Stars can also have different sizes, like giants and dwarfs. So if you look at a night sky and see lots and lots of stars, you see billions of stars, at least through telescopes, that are in all stages of their life cycle. They're being born in explosions inside nebulas, which were previously exploded stars, where gravity is beginning to contract the debris back together again until it reignites in fusion and becomes a new star. And then that star will eventually wear out, and it can either cool down and become a big chunk of matter, or else it can begin to contract as it uses up its energy, and that contraction can cause it actually to begin to shrink, collapse in on itself, and reignite. So there's all kinds of things that can happen regarding stars. And looking at the colors is a very, very helpful way to begin that study. You find in God's creation that he always gives you very easy level 1 discoveries to make, like the different colors of stars, so that you're ready for the next level of investigation, which takes you to a deeper understanding. And then that enables you to get to the next step. Creation is filled with stepping stones of learning about phenomenon in creation in greater and greater detail. So thinking about black body radiation and thinking about the ultraviolet catastrophe, so both of which will be talked about in greater detail in AP Physics, we're going to go to the person who probably contributed the most to our, and got us on the right track to understanding why the intensity did not increase as the wavelength decreased, but instead fell to zero, the ultraviolet catastrophe. And the person we'll look at is Max Planck. And it's interesting to see how many physicists during the turn of the late 19th into the early part of the 20th century were German, probably the most highly educated, most advanced culture, most prosperous nation. And of course, that played a toll on their worldview. It was a very religious nation. The Lutheran Church was very, very strong. But as they became prosperous, they began to ignore and drift away from their Christian roots in the Reformation with Martin Luther back in the early parts of the 16th century. And they became more and more secular. And that secularism is a major contributing factor to especially the rise of Adolf Hitler in the 1930s, and then World War II and the Third Reich, and Nazism and fascism, and the catastrophes that resulted from that, such as the Holocaust. So anyway, Max Planck, and I mention all of this because many of these Germans that you're going to hear about did have a Christian upbringing, at least early in their life, and to various extents, many of them abandoned that Christian upbringing. So Max Planck was Lutheran early in his life, but later on he never gave up the idea that there had to be a God to explain the precision and the intricacy and the mathematical intelligibility of the universe, but he did not believe in a personal God. So we would call Max Planck a deist. He had some very interesting observations that I think we could agree with. For example, he said, science cannot solve the ultimate mystery of nature because we ourselves are part of the mystery we're trying to solve. So we are inside this nature that we are trying to explain and understand. In other words, ultimately, you're going to have to look outside of creation, outside of nature, for the bottom line explanation of why creation is the way that it is. In other words, that would be a transcendent God. And Planck got the transcendent part of God. He did not get the immanent, that is to say, the personal God, as best represented, of course, by Jesus Christ becoming man. Another one of his ideas was that matter comes from consciousness, not consciousness emerging from matter. So even today, the materialist, the person who doesn't believe there is anything in the spiritual realm at all, must explain the mind and the consciousness just through biology and just through matter. Whereas that's really increasingly becoming impossible because rather than the mind being something that emerges from the brain somehow, we more and more realize that the mind cannot be explained by the brain. The brain might be the infrastructure in which the mind and the consciousness operate, but the mind and the consciousness are much more than the brain. And so therefore, this whole idea of matter must come from a mind. In other words, the creation is something that comes from the mind of God. We often call this, in a more generic sense, intelligent design, which is a position held by many scientists, both Christian and non-Christian, that there has to be a designer. That may lead them to the God of the Bible, or they may come up short. And then one last interesting thing about Max Planck is that he said science advances one funeral at a time. In other words, some ideas become so entrenched that you really can't get away from them until the people that are embracing that idea finally die, and then new ideas can take its place. And we're finding that out right now, as a matter of fact, with the ideas of Charles Darwin, that as the main proponents of Charles Darwin and neo-Darwinism begin to get old and begin to die, it's making room for better ideas, newer ideas, because Darwin's ideas of natural selection acting on random variations within a population, and then the neo-Darwinism incorporated the genetics, and the diversity or the new information had to be explained by mutations. All of that is now being rejected and is understood to be totally inadequate. So that was several tangents. Let's get on with our story. And as we said before, energy is proportional to frequency. So we can get rid of the proportional sign by introducing our constant, Planck's constant. And then we can actually have whole number multiples of these energetic photons, and that's where the n is. Can be a 1 or a 2 or a 3 or 4, but Planck said it can't be anything in between. It can't be fractional. In other words, it's quantized. And you can see we're laying the foundation here for quantum physics, quantum chemistry, and a quantum explanation of energy itself. Planck's constant is extremely small, 10 to the minus 34th, which is why you don't see these quanta, these jumps, these steps when you say put your foot on the gas pedal in your car. It feels very, very smooth as you accelerate. It doesn't feel like it's doing this as you get one quanta, then the second quanta, then the third quanta, then the fourth quanta of energy. You don't see that with big things like cars or when you're running or when you're throwing a baseball. But when you talk about photons, you see that you either have one photon or two or three or four, and the energy is not, let's say, an analog, but it's sort of digital, right, like this second picture. It comes in chunks. It's not smooth at the quantum level. So this is the equation you should be very familiar with right here when we're talking about a particular photon's worth of energy. This is Planck's equation. Now Planck, we assume as Planck did that there must be a distribution of vibrations. So you can have many photons vibrating at many different frequencies. But most of those vibrations, or the majority of those vibrations, will produce the majority of the light and give the characteristic color of that particular batch of photons, even though there are other photons that might be present. So you get a mixture of these. But the energy itself is quantized. Now, Einstein comes along and is able to take Planck's work, and I've heard Planck's work at the same Max Planck, and he was able to use this idea of quantized energy to explain something called the photoelectric effect. Photo, of course, means light. Electric has something to do with electricity, which implies electrons, as you'll see in a minute. And the photoelectric effect is a property of light that, interestingly enough, cannot be explained by thinking about light as being a wave with crests and troughs and wavelengths. If we think about light moving in a straight line, called rectilinear propagation, we know that you can think about particles moving in a straight line. I'm going to draw a little chart here. We can have the particle model for light, and we can have the wave model of light. The particle model of light goes actually back to Isaac Newton. And the wave model of light goes back to a person who lived about the same time, not as well known, named Christian Huygens. And of course, Newton was extraordinarily famous. So when we think about rectilinear propagation moving in a straight line, Well, particles move in a straight line. Think of a billiard ball going across the top of a table. And waves can move a straight line. Think of a wave front advancing towards the beach. And then when we think about reflection, reflection can be explained by particles like a billiard ball bouncing off the cushion. And you can predict the angle. The angle in which the billiard ball strikes the cushion will be the angle that it rebounds off the cushion. Well, it turns out waves rebound off a barrier the same way. Then we have something called refraction. This is reflection, so it would be an L. Refraction is the bending of light as it goes into a denser medium. And for a while, Newton had a model for that, but it didn't work. We talk more about this in physics. So Newton's particle model could not explain refraction, but the wave model could explain refraction, that light bends when it enters a denser medium. And then you have interference. Obviously, two particles can't pass through each other, but waves can pass through each other. If you're watching waves being created by motorboats out in the lake, and you can see the waves pass right through each other. And when they pass right through each other, you might get a temporary reinforcement or a temporary cancellation of the waves. But then when we come to the photoelectric effect, we find out that the wave model can't explain that. And the particle model can. So the point being that up until the photoelectric effect in the beginning of the 20th century, everybody pretty much resigned themselves to the fact that light was best explained as being a wave, and this is one of the few areas where Isaac Newton was wrong. And then along comes the observation of the photoelectric effect, which I still need to explain, and that cannot be explained by the wave model, but it can be explained by the particle model. So neither model is perfect. We kind of need both models depending upon the experiment. So think back at my definition of light. Light is packets of energy called photons, which have wave-like characteristics. And you can have high energy photons or low energy photons, but it is a particle. It is a packet. It is a chunk of energy, and that energy is proportional to its frequency. So what is this photoelectric effect? In the photoelectric effect, which explains all the different types of technologies, like when you walk through a door, there could be a security system in place that triggers an alarm, or you walk into a door and there might be a photo sensor that detects a change in light that activates a switch. You might know that there is not a person who every night turns on all the lights on the top of street poles in neighborhoods, and then in the morning that person has to turn them all off again. That's all controlled by a photocell that's at the top of every light on every pole. And that photocell, and you might have a light that comes on automatically, even on your porch. There could be both a motion detector and a photocell to sense when it starts to get really dark outside, the light comes on automatically, and then when the light of the atmosphere begins to increase as morning comes, it'll turn the porch light off. So that's what this is. This is a photocell. And so the wavy line here indicates the incoming light. And it strikes a piece of metal. It doesn't have to be curved, but to fit it inside of this little dome-shaped object, we curve the metal. And when the light strikes the surface of this metal, you might recall that the electrons on metal are delocalized. Metal is not like ionic solids, nor is it like covalent solids, but metals have delocalized electrons. They are neither shared nor exchanged, but they're loosely held in place by a matrix or a crystalline structure, if you will, of nuclei. And so these electrons, being loosely held, can be ejected. So when the light comes in and strikes my metal surface, when it comes in and strikes the metal, it might eject an electron. Now, before it does that, the light can be coming in, and we get absolutely no indication in our meter of any electricity, of any complete circuit. There's a break in the circuit because the blue wire here is connected to the metal, and the red wire here is connected to this anode, this little post. And it's a broken circuit. Now, if the light is low frequency, which means big wavelength, we have big wavelength, which means we have small frequency. Use the letter F here. And so small frequency means low energy. Low energy coming in, and that energy is not enough to dislodge an electron from the metal. Now, if we have high energy, in other words, this is going to be a low wavelength, but a big frequency, so therefore it is big energy. These photons pack enough wallop, have enough energy, that when they strike the metal surface, it can dislodge an electron, and the electron, being negatively charged, can be attracted to the positive anode. And this positive anode then attracts a negative electron, and that's what's going to complete the circuit. That charge is going to go this way through the meter, and we're going to see the meter is going to register that we now have a complete circuit. Now, if we increase the intensity of the light over here, but it's low intensity, we still don't get any current. In other words, by having very, very bright, big wavelength, low frequency light, we still don't get much, any complete circuit. But over here, if we have really, really bright light, as opposed to dim high frequency light, we have intense high frequency light, then we get even more current than we got before. Here's an analogy. I can shoot a spit wad through a straw at my favorite student, you know who you are, and I can shoot spit wad after spit wad after spit wad, and those would be like low energy photons. They don't do any damage. They might be disgusting, but even if I did 1,000 of them as opposed to a few of them, it's not going to make any difference at all. However, if I shot a BB would be like a high energy photon. It only takes one BB and it could leave a welt in the skin. And I know this because one of the stories from my dad, when he was a boy, he received a BB gun for his birthday, and he promptly shot my uncle, his younger brother, with it, and he got in big time trouble, as he should have, for that. I, of course, never, ever got in trouble growing up as a boy. That was an intentional cough. So not only would one BB dislodge an electron because it packs enough wallop, enough energy, but many BBs would do even more damage or dislodge even more electrons. And so the point being is that at a certain point you don't have enough energy. You can shoot the spit wad higher and higher. You can have none of them just have enough energy to dislodge an electron. In other words, it takes a certain amount of energy before you start dislodging an electron. We call this, by the way, ionization energy. Ultimately, when you have enough energy to knock an electron permanently loose so that it escapes the nucleus altogether, you have created an ion. And we call this energy the ionization energy. But you have to pass a certain threshold for that to happen. So I hope you understand the photoelectric effect, because it's very important. And it can only be explained, as you can see, by thinking about light as being made up of particles of energy. Some of them might have low energy. Some of those particles might have high energy value. Now let's look at this problem right here. We can talk about the energy per photon simply by knowing Planck's constant and by knowing its frequency. We can calculate the energy of that particular photon. And as you might expect, it's a very, very low energy. You can see that that's 10 to the minus 19th joules per photon. So it's not uncommon, and you'll be doing this on your test and in your homework. You'll multiply by Avogadro's number. And so now the photons are going to cancel out. The photons cancel, and now you have your energy per mole. And your energy per mole now is something that we can measure in the laboratory, 175 kilojoules per mole of energy from a mole of photons which have this particular frequency. Now, this energy, we should point out, the blue light photons, notice it has a low wavelength, so it's going to be a higher frequency, 300 kilojoules per mole. And this particular energy is in the range to break chemical bonds. And of course, that's what we're very interested in chemistry and in biochemistry. This is the value that the bonds between parts of protein molecules have. And so this is the kind of energy that can break up a protein molecule into its component amino acids and even more than that. If we have a higher wavelength, we move towards the red end of the spectrum, we're going to have lower frequencies, and this is going to show up as infrared heat. And this heat is not enough energy to break these bonds, which is a good thing, because if you experience a little bit of heat on your skin and it begins to break down all the proteins and other kinds of molecules in your skin and in other places in your body, that would be very, very destructive, and you would hate it when that happens. All right, this is a good time to review this material and see if you can check for understanding by doing this section right here. I'm going to make sure I didn't skip anything, and we're going to pause right there and pick it up in the next screencast.